Welcome to Full Momentum, an HEC-RAS podcast. I am your host, Ben Carey. We are here on episode number 32. Joining me, as always, is Chris Goodell. And we also have a very special guest joining us today. Before we introduce Isha, Chris, I do need to give you a hard time about your Oregon State Beavers coming up a little bit short from where I know you kind of had wanted them to be. So both,
yeah.
I think Gonzaga basketball and Oregon State didn't get to where we wanted them to be this year.
And just to be clear for everybody, we're talking about Oregon State baseball. Basketball is not very relevant these days at Oregon State, but baseball usually puts together a really good team. And yes, it was disappointing. Wish we could have gone to Omaha. We got to the Sweet 16, the Super Regionals, and just ran out of gas. And you're a big baseball fan, Ben. So you tell me, like, when the hitting just goes away, is it more the batters just run out of gas, or they just run into a great pitcher, or a little bit of both? Or it's frustrating when you can't get bats on balls,
Yeah, I think, typically what you see in playoff level baseball at in college or in pros is that, the good pitching really starts to come out. And I think part of that is because, it's kind of do or die situations a lot of times in those postseason games. So you're putting your best pitchers out there. And I think it's pretty well known that pitchers will ramp up their level of effort in the playoffs. So usually you get a few miles an hour extra on those fastballs. You get a little bit more break on breaking balls. So this is not a baseball podcast, but I agree with you, Chris. Typically late in the season, sometimes your pitching wins. So
yeah, I think that's probably what it was. And just to wrap it up, I'll just say, hey, this was the end of an era of the Pac-12, and Oregon State got to play the very last game of the Pac-12, being that super regional baseball game. So in a sense, we were the last team standing. Moving forward, now everyone's in different conferences, and things will be really weird from here on out. But
rest in peace, Pac-12.
Yep, exactly.
Well, I got great news for you, Chris. If you want to watch more baseball this summer, there's another really good Northwest baseball team that's playing good ball up
in the
Seattle.
Pickles. You're talking Seattle. I thought you were going Pickles. Okay.
The Portland Pickles may also be playing well, but the Seattle Mariners are in first place in the AL West.
Yeah,
so
I may have
feel free to hop on board.
Yeah, I may have to do that.
Awesome. Well, for everybody who's watching the episode here on YouTube, you recognize that we have a guest with us today. So Isha is a H&H engineer that works here at Kleinschmidt. She's been with us for a while now, and does some really, really cool stuff within our group, specifically within the HEC-RAS kind of realm of our group. And so we thought that she would be an awesome guest to have on. So Isha, for the first time, welcome to Full Momentum.
Thank you, Ben. Well, I just wanted to say that I know y'all's favorite college sports teams suck, but my Texas Longhorns did go to the football playoffs. So there's that.
Absolutely, yeah.
I mean, it's hard to compete with your Texas Longhorns, across all sports. But they do a good job on color scheme. So it's not the perfect color orange, but it's close enough that I can get on board with Texas.
Now, if we want to pit the Oregon State fan here against Texas, what we would really say is that Texas kind of was the first stone to fall in the breaking apart of the Pac-12, because Texas and Oklahoma going to the SEC was the first big move that kind of started this whole giant realignment thing. So not saying it's true. Texas's fault, but it's kind of Texas's fault.
It was, like a mouse whisker away from Texas and Oklahoma being in the Pac-12, Isha. Then we really could have gone at it.
That would have been fun.
Yeah. Billion conference rivalry, but yep. Didn't come to be, and here we are. Yeah.
So Isha, if you want to give a brief kind of introduction to yourself and how you ended up here at Kleinschmidt and how you ended up here on the podcast. So.
Yeah. So I joined Kleinschmidt, I think, almost 5 years ago. I was wrapping up grad school. I went to the University of Texas, of course, for undergrad and grad school for water resources engineering, and really wanted to work with Chris, work in Portland. So I moved out here in 2019 and started working at Kleinschmidt. Since then, I feel like I've been working on a lot of really cool RAS projects with help from Chris and Ben, and then learning a lot on the job. But yeah, super happy to be here. I think some of my favorite things working at Kleinschmidt have been all the modeling, but also getting to play around with a lot of coding stuff in my free time and on projects. And so that's been something I really enjoy doing. Certainly always have a lot to learn about it, but it's a really cool kind of way to branch out. So
I still remember when we interviewed Isha, and her resume was stellar, and looked really good, and that's the primary reason we brought her forward for an interview. But then when she got on and we got to have a conversation, we were like, wow, she is really polished. She's got great communication skills. This is like a rarity in the world of engineering, super smart, good resume, and can communicate. So we were like, okay, yeah, we have to hire Isha. And then we didn't hear from you for I don't know, a long time. We're like, oh no, she went somewhere else. So I'm glad that wasn't the case. Although I think you were probably shopping around a little bit, but hey, that's okay as long as you ultimately came to Kleinschmidt.
Ended up on the right place.
That's
right. Yeah.
Yeah, and Isha has brought a lot of really cool, unique skills to our H&H group. I know, Chris, before Isha, there wasn't a lot of folks within our group that knew a lot about coding and how to potentially utilize that skill set within, an H&H modeling realm. But Isha's brought a lot of that to our team, and that's going to be part of the special topic that we get into today when we get into the primary topic. But before we do that, I do want to start off with kind of a fun segment. And this idea came from a listener to the podcast, and somebody who apparently is pretty active within the RAS community space. Ryan Troy had the idea of, what are the full momentum 10 commandments of HEC-RAS modeling? He threw out a couple of good ideas there for what he would kind of start his list with, and so we thought, hey, that's a cool topic. Let's bring Isha on to contribute and kind of develop our 10 commandments of HEC-RAS modeling. So we each came up with 3. Chris, you had that bonus 4th to close us out to 10. So why don't we go through one at a time and just share what our kind of core foundational beliefs about HEC-RAS are.
All right, so mine are fairly general, non-specific, kind of high-arching commandments of HEC-RAS modeling. Can really be applied to just about any software, but super important in HEC-RAS modeling. The first commandment is know your objectives. So know why you're building your model. What's the purpose of it? What are you using it for? What are the questions you're trying to answer? And if you keep that in mind throughout the entire process, you're going to end up with a much, much better model, and probably not have it crash on you as much.
Yeah, very good. Well, that commandment goes really well with Isha's first one. So Isha, what's yours?
My first one, similar to Chris, kind of defining your objectives, I think is checking your time step. I feel like that is such a crucial part of the computations. It makes a big difference sometimes if you don't pay attention to what your time step is, and it kind of got to ensure that your model is doing what you think it's doing. Big part of that.
That's a good one. I have a funny story about that. So in earlier versions of HEC-RAS, maybe before 2D came out, but certainly people were doing unsteady 1D modeling with it. The default time step was 1 hour for HEC-RAS models. And so people would come in and they didn't know that the time step was something they had to change. And so I can't tell you how many times somebody would send me their model and it just crashed right away. And it was simply because the time step was left at the default of 1 hour. And then if I just changed it to whatever it needed to be, 1 minute, 30 seconds, whatever, it ran perfectly. And sometimes these poor people spent hours or even days trying to figure out why their model's crashing, and it was just a time step thing.
Yeah, which is why it's such a good commandment when it comes to using HEC-RAS. So, my first one is you should always use distinct naming convention for plans, geometries, and flow files. This is another one that we see all the time when we get models sent to us. And to be fair, I put my hand up. I do this at times too. If you're just trying to bang out a quick model, get some stuff running, it's a lot easier to name it plan 1, geometry 1, flow file 1 than to give it distinct naming conventions. But man alive, Isha, you can attest to this. If you have a big model with a lot of different runs, having very distinct, clearly named plans, geometries, and flow files will make your life so much easier as a RAS user. So I think that's a good commandment for everybody to abide by as they're developing their RAS models.
Yeah,
really been. Go ahead.
Yeah, go ahead. Go ahead, Isha.
It's like just that it's really been something I've like tried to start nailing down, because there's no worse feeling than being like, what does this plan do?
Exactly. Yeah.
Yeah. Can I add a kind of an add-on to yours too? And that is keep all those files in the same folder. I don't know why. It seems like I've been seeing this a lot lately.
You're breaking into my second commandment, Chris.
Oh, I'm sorry.
You didn't review you didn't review our own 10 commandments, man.
Forget it. I did, heretic. But, yeah. I did. I just saw terrain. I'm sorry. Okay, I'm getting ahead. All right, I'll shut up. Okay.
All right, Chris, what is your second? What is your second commandment?
Oh, man. Okay. This is another kind of general one, but keep it simple. So keep your model simple. Ben and I talk about this all the time in the class that we teach, that you keep your model simple, build it in stages, don't add things in that don't need to be there. Keep it nice and concise. That's going to make your model run faster. It's going to be easier to troubleshoot, and you're just going to have less problems overall. Keep it simple. Basically, what I like to tell people is build your model just to the point where it can answer the questions you want to have answered, and nothing more than that.
Yep. Good.
Keep it simple. And I left the other S off, the KISS principle, because I don't want to call anybody names.
Not in the Ten Commandments.
What's that? Yeah, that's right. We have to have a friendly 10 Commandments here.
All right, Isha, what's your second?
My second one is to not rely on the green finished computations message or on the full blue bars. Always kind of look closely at your results, look at those stage and flow hydrographs, look at RAS mapper, look at your Courant numbers, profile plots, all that good stuff, to make sure the results are really doing what you want them to and think they're doing.
Yeah, this one's really important, particularly for 2D modeling, right? 1D modeling tends to give you better output messaging in terms of if there's errors or issues, but you can have a pretty poor performing 2D model and not realize it if you're just relying on those two things. So that's a really good one, Isha.
Yep.
Yeah, really good.
My second one is to Chris, you were
I'm sorry.
You were a prophet here. You were a prophet, predicting
right.
what was coming here. But my second one is to include all of your model source files inside of your model file structure, particularly when you zip up and send that model to somebody else. There are, again, so many instances in my experience where I'm reviewing a model that came from somebody else and it doesn't have really important basic pieces of information included in that model when I open it up. And that's because of the fact that they didn't have the terrain file or the projection file included in that same kind of model structure. And so when you go to zip everything up and send it out, those links get broken and you're missing really, really critical information. So always include everything that's in your model should be kind of within that modeling structure. Now you can have individual subfolders for things like terrain data or GIS data, but it needs to kind of all be within that same model folder structure. So.
Yeah, here's a little tip for everybody too. If you use the zip or archive projects option under the file menu item, the main RAS window, it's a good way to send projects to somebody. But if you do that, open it up, unzip it before you send it just to see what it looks like. If it has a folder in there that says external dependencies, that means you've got files outside of your folder structure, and that's going to really screw up the person who receives your model. So, yeah, that's a great one, Ben. Sorry, I stepped on your toes there and gave everyone a little preview, but it is a really good one. And I see people breaking this commandment a lot lately. I don't know what it is, but that there's this desire to kind of compartmentalize different files in different folders, and it's just, don't do that. Just put it all in the one folder. And like Ben said, you can have subfolders too if you want.
Yep. Yeah. What I always like to do is zip up the folder, bring it onto my desktop, open it up, and then open up the model there. And if everything's looking good in terms of the file structure, then I know that if somebody else does the same thing, they'll be able to see it. So it's a good little kind of self QA/QC. All right, Chris, what's your third commandment? Our seventh as a group.
Read the manuals. It seems pretty obvious, and I'll be the first to admit I'm not a manual reading guy. Whenever I get a desk to build at home, or a bookshelf or something, I don't read the manual. And but in this case with HEC-RAS modeling, the manuals are so good and there's so much information in there. Read the manual. If you're running into trouble, you're not sure how to do something, get in there and do a Control F to search on whatever you're looking for. But there's a lot of stuff in there that can be really helpful. And I recommend too, if you can figure this out, get a full PDF of the manuals to bring onto your computer, because it's, at least in my opinion, it's a lot easier to search around when you have the full PDF versus the online version. It's kind of segmented into little just mini chapters here and there. So it's a little harder to search through the whole manual that way. But that's just me.
Good. Well, I might have read the manuals to pull out a trivia question today for the end of this podcast. So,
all right, we'll see who actually reads the manuals then.
Exactly. All right, Isha, number 8.
Number 8. This is one that I feel like I have made a mess on multiple times. So my number 8 is double and triple check your datums when you are pulling data into RAS. Especially your vertical datums. Horizontal datums are usually kind of, make sure you have the right one, but once you set it, it should be pretty straightforward. But the vertical datums, you're pulling data in from a bunch of different sources, document it all, write it in the descriptions. It makes your life way easier.
Yeah, especially I think like you noted there, Isha, if you're using multiple data sources, this commandment becomes exponentially more important. If you're using one data source, it's still important to check that datum, but worst case is your results are off by, a set number of feet. For instance, if you're using a wrong datum or a different datum than what you thought you were using, but when you're combining different data sets, that's when things can potentially get pretty hairy. So really, really important.
Good one.
Number 9, and my last one before we turn it over to Chris for our 10th commandment, and that is conduct sensitivity analysis on uncalibrated model parameters. So as you're building out your models, in many cases, hopefully in many cases, you have calibration data that you can use to refine and build some confidence in your uncertain model parameters. This could be values like Manning's N values, turbulence coefficients, other kinds of energy loss or important parameters that affect the results within the program. But if you don't have calibration data, or if there's particular model parameters that you weren't able to calibrate with the calibration data that you have, it's really important to run sensitivity analysis on those to really understand what the results in your model mean, what the uncertainty of those results are, and that's going to make your presentation of those results to your customer so much better, and it's going to make you a better modeler overall.
Yeah, right, Chris, that's a good one. Yeah,
close this out.
So last one is report bugs. Okay, so we are a community of HEC-RAS users, and they're exponentially more users out there than there are developers on the HEC-RAS team. So the developers can, only catch so many bugs, but it's inevitable that we are going to find bugs when we're using the software. So please, 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 if you do run into what you think is a bug, send a bug report to the developers. If you don't know how to do that, go to their website, HEC website, and you'll see a place for a bug report. If they don't get right back to you, don't think they're ignoring it. It's likely they're busy and they probably have a list of them they're working on. And if you're still not sure, get a hold of me, send it to me, I'll forward it on to them. Because I think that just makes the whole software experience better for everybody. And, hopefully can avoid some serious errors and inaccuracies in models. So, and there have been some big ones in the past, and I just ran across one recently. I won't mention right now, but I have already shared it with HEC. So anyway, yeah.
Yeah, good. So to review the full momentum 10 commandments of HEC-RAS, we have thou shalt know your objectives, keep your model simple, read the manuals, report bugs, check your time step, don't rely on the green finished messages and blue bars, look at your results in more detail, double check your datums, use distinct naming conventions, include all model source files when you zip and send a model out, and conduct sensitivity analysis on uncalibrated model parameters. I think that's a pretty good list. If you do all those things, you're going to be in good shape.
I think that's a really good list. And I'm sure, our listeners out there, if anybody's still tuning in, is probably has some other ideas for what could be on this list. So, yeah, let us know. And I think, Ben, we ought to make some official stone tablets to hang on the wall behind you for the next episode, so that we can continue to remind everybody what the 10 commandments of HEC-RAS modeling are.
There you go. Good. Well, thank you, Ryan Troy, for that idea. That was a fun little segment. And thanks, Isha and Chris, for your participation there. So, all right, let's jump into the primary topic for today. Before we do that, I do want to just give a quick shout out to the sponsor for this episode. That's our firm, Kleinschmidt Associates, who is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. So thank you, Kleinschmidt, for sponsoring our discussion today and allowing us to share silly things like the 10 commandments of HEC-RAS, but also cool, more in-depth technical topics like our discussion today on HDF files. So we wanted to talk about HDF files. This is an episode that we've been wanting to do for a little while. Isha has done some really cool work around this topic within our group, so we thought she would be a perfect guest. But Chris, why don't you go ahead and kick off the discussion by giving everybody kind of a high-level overview on what is HDF, what are HDF files?
Yeah, so HEC-RAS historically, before version 5 came out, was made use of two different output files. They're called for lack of a better name, the output file, that's the O file, and then the DSS file. The O file contained a lot of the post-processing data for 1D models, and the DSS file kept all of the unsteady time series data and some other stuff in there too. But if you look at a project folder like I'm doing right here, this is one I'm working on right now, but you can see that we have no O files. And why do you think that is, Ben?
Ooh, you're triviaing me before the trivia.
Yeah.
Is it because
there's Isha, if you know.
Is it because there's no 1D elements?
Oh, 2D.
I take it back. There are O files.
Yeah, I was gonna
sorry,
say,
I messed you up.
I was confused because I was like, because no output files would mean no 1D results, right?
That's right. Yeah.
And this is a 1D. This is a 1D 2D model. So
this is a 1D 2D model. So yes, you're right. Sorry, I kind of flubbed that. But yeah, there are output files, but that is because we do have 1D elements for our 4 different plans here. And so this again will only contain 1D output, and it's all the post-processing stuff. There's also DSS file. This is another output file that we have, and that keeps mostly time series data. So if you have an unsteady 1D model or 2D model, you're going to see data sent to the DSS file. What's interesting is if we look at the unsteady flow analysis window, the detailed output interval that we see every time we hit the compute button, that sends your output, your detailed output, post-processed 1D output to the O file. So this is where the O file is being built. And then the hydrograph output interval is where the DSS file is being built. And then the mapping output is the third and newest output file called the HDF file. And so if you look, kind of scan through here, you see a bunch of .hdfs in here. And RAS started using this for, I think, in version 5, and it was specifically because models are getting much larger now, being 2D and taking longer to run. And the HDF file is built for that. It's built for fast data processing and data exchange. And so that's why we have the HDF file. And you can see that there's an HDF associated with each of the plans. So here we have plan 1, and then we have our plan 1 HDF file. This is our output HDF file. This is when you go into RAS Mapper and you look at your velocity map or your depth map. Those are all built off of data in the HDF, the plan HDF file. There's also a geometry HDF file, and this is strictly your geometry input data stored as an HDF file. So we have our regular geometry file and we have our geometry HDF file. The geometry window reads this file, the GO1, and RAS Mapper reads this one, GO1.hdf. And so when you're in RAS Mapper and you save your geometry, it actually saves a new GO1 file. And likewise, when you're in the geometry window and you save your geometry, it saves a new geometry HDF file. So there's some other HDF files associated with the unsteady flow, and even your terrain has an HDF file as part of it. But I just wanted to point out they're all over the place in your file directory, and those are output files. And you can look at HDF files, but you need a specific kind of software called HDF View. There's probably other ways out there, other software that'll look at HDF files, but the HDF View is the one you can get right from the web. It's free. It's called HDF View. If you just Google that, you'll find it. And this will allow you to look at HDF files, HEC-RAS HDF files in this tree format. And you can kind of drill down to find out exactly what you're looking for. And if you're looking for results, you usually have to go results, unsteady, output, output blocks, base output, unsteady flow time series, 2D flow areas, and then finally your plan name. And then you'll see base velocity and water surface, which, by the way, are the only two things computed in a 2D model. Did you guys know that?
By default.
Well, these are the only two things that are actually computed in the unsteady computations. Okay. Everything else is post-processed off of that. So you get your face normal velocities and your water surface. And so with these two things, you can create just about anything you can think of. And this is why we brought Isha in here, because she has an expertise in programming using Python and interacting with these HDF files. And which I really love, because this makes life a lot easier in some cases, and quicker and faster and more precise. So if you go in and look at, it's kind of interesting. If you look at one of these records, we'll look at water surface. It pulls up you got to double click it. And where is it? It's hiding somewhere on my computer, I'm sure.
Chris, real quick.
There it is.
Folder under 2D flow areas, it's not your plan name, it's your 2D area name.
Oh, yes, you're right.
Yep.
You're right. Yep. Because it does say 2D flow areas. Yep, that's right. That's your two. Yeah, I just happened to name that my plan as well. That's the confusion. So
you this broke one of our commandments to not have clear to naming conventions there. Playing out in real time.
Oh gosh, I couldn't have scripted that any better. Okay. Do as we say, not as we do. Okay. All right. So yeah, you double click on any of these records and you get a table of numbers, and a lot of numbers, a lot of big numbers, and you can scroll over and see everything. And unfortunately, the HDF viewer, and I don't know if this is on the RAS side or it's just the software, the HDF viewer software itself, but it doesn't tell you what the numbers on the the y-axis versus x-axis are in this table. So you kind of have to either remember or refigure it out every time. But I know this is time step over here, and more precisely, it's your mapping output interval, because that's how this data is stored, by your mapping output interval. So these are all your mapping output intervals. And then across here is your cell number from 0 all the way to 3361. So I know I have 3,361 cells in this project, and I can get, for every mapping output, I can tell you what the water surface elevation that was computed for each of those is. Now, you can imagine this is trying to find, exactly the water surface at a specific location. You have to figure out, okay, what cell is that, or what group of cells, and you have to come in here and kind of scroll around. Or you can do what I do and call Isha or your favorite Python developer and have them write a script that'll do it for you very quickly.
Now, before we get into scripting, just a couple questions for those of us who are novices in the scripting world. Chris, the RAS mapper, when it's basically plotting depth, velocity, dynamic maps, static maps, is it accessing the HDF files to do that?
Yes, it is. And that, I'm glad you brought that up, because when you go to animate your model and you either press the green play button or you just manually animate, every refresh of the screen, whether it's a velocity map or a water surface or depth map, it doesn't matter. Every refresh of that screen, RAS is accessing the HDF file, this thing that you see right here. It's pulling the data out. It's computing whatever it is for every single cell or cell face. Then it's interpolating between them, and then it's putting that on a map. That's all done in a fraction of a second. And part of the reason that can be done so quickly is because RAS uses these HDF files, which are data storage files that are very, very quick to work with. So
yeah, and you'll also notice that as your models get larger and larger and longer, your HDF files, the size of those gets more and more significant. So
yeah, that's a really good point. In fact, yeah, if you ever have a really large 2D model, it's almost a guarantee the biggest files are going to be your HDF files. Now these, because this is a small model, these are pretty manageable. Although even 10 years ago, I would have thought, oh, that's a big file. But nowadays in RAS world, these are small manageable files, but these can quickly get up into the gigabyte size. So that's a good plug for keeping your output interval smaller. Or sorry, not smaller, bigger. So you have less output intervals. So if I, open this up and we go back to this window here, this output interval, the smaller you make this number, the bigger your HDF file is going to be. And of course, the longer the simulation time and the more cells you have, the bigger your HDF file is going to be also.
Yep.
Yeah.
Yep. So
I was working on a model. Sorry.
Go ahead. Yeah, no, go ahead, Isha.
I was working on a model recently where every time we opened the HDF file in HDF view, once you opened a table, it would crash. So you can only look at your table. But if you want to look at a different table, you have to open it all back up again, just because the HDF file was super, super big.
Oh, really? Oh, was that do you think that was just a computer limitation, or there's something with the HDF viewer that wasn't letting you
I would guess it's a computer limitation, but it does kind of push that. So something to keep in mind.
Definitely.
Yeah, I mean, you can, with these large large HDF output files, you can quickly overwhelm your own computer. And I get this a lot from people who say, but RAS is just not running. It's crashing on me, or it's just it's halting mid-run or something like that. And then you see something like something to do with file size or access issues. A lot of times that's because you just basically filled up your hard drive and there's no more space left. So be careful about that.
Yeah. A question I have for you, Isha, and this might be a good opportunity for you to share your screen, is just around some of those additional options that you can get in your output that can be stored in the HDF files. I know Chris talked about the default ones that are computed, but there's a lot of other information that you can have post-processed into your HDF files, I believe. Do you want to tell folks
Yeah.
about kind of how to access that and when you might want to do so?
Yep. I can share my screen if you don't mind, Chris.
Yep.
So there's a lot of cool information, as Ben said, that can be written to the HDF file that isn't normally written. So Chris referenced usually is just the face velocity and the water surface elevation. But there's a lot of output that you can maybe want out of your model and you want to read using the HDF file. So you can find that if you go to your unsteady flow analysis window, options, output options, then might have written some restart files and such. This detailed log output will write to the O file, if I'm not mistaken. But when we start getting into here, we start writing to the HDF file. You can, I know here you can definitely write to the HDF file, but computational level output, if you want info at every time step, that's something you can do. And I know Chris and I have done this on some projects where we weren't able to capture like a peak number in the regular output. So kind of bracketing where we think that's going to happen and writing computational level output. And then we have this entire list of HDF5 write parameters. So HDF5, name of the file, a lot of different duty variables to be written here. So these are all things you don't want to write unless you need them, because they do make your files pretty big as you start clicking more and more of them. But there's a lot of really interesting information here. So I know I've used the hydraulic depth, invert depth sometimes. Cell velocity is a big one. So this will give you the cell X and Y velocities in case you need some directional information.
Mm-hmm.
Cell volume.
That one in particular, cell velocity, is an interesting one because, Isha, correct me if I'm wrong, we've used that XY velocity in other model types, such as an agent-based model that needs that sort of XY component to our output velocity. So it's a way. Sometimes there's other programs that require more detailed information than what we can provide with from RAS output by default, but we have a little bit more flexibility here.
Yeah, absolutely. So these are all just really, really interesting things that RAS doesn't need to finish the computations, but it is something that it can compute as it goes along, and you can get some more information out of the model. I certainly haven't used a lot of these, but if you have a use for them, or if you have, a downstream use for them, definitely worth checking out.
What is that exclamation like warning message button up there? What is that? I've never clicked on that.
Yeah, let's find out together.
Okay. Learning things
I've looked
on
at
the
this
fly.
before, but it's been a while for sure.
Okay, this is making really good pod, us all reading this. So
it's okay. I think it just has to do with the written velocity at individual nodes, because that velocity is not actually used, right? It's post-processed. So I think it's just a kind of a warning. I don't know why they give it for that one and not some of the other components, but yeah. Maybe just because it's common.
It's like up here. It's not even.
Well, maybe that's because Chris, correct me if I'm wrong, there's other 2D software out there that actually computes velocity at nodes and not at cell faces. Is that right?
Yes,
I believe Flow2D does that.
Yeah. Yeah, I'm not sure.
Anyway, we can cut that out. But I think it may be because of the fact that there are velocities computed at nodes for other softwares, and so if there's somebody who's used to using that, comes in here and sees that you can get face point velocity, they just want to be really, really clear that that's not something that's computed.
Yeah.
Yeah.
That's
Yeah,
my
I
go.
mean, if you forget everything else, remember that RAS in a 2D area only computes water surface elevation for each cell and face normal velocity for each cell face. Everything else that you see is post-processed off of those two variables.
Yep.
Yep.
One other thing I want to point out here is the very top option under optional HDF output parameters, which is the write the warm up time steps to output. This can be helpful, particularly if you have a model that's crashing immediately when the model starts to run, but it's getting through your warm up time. That sometimes allows you to view those results during the warm up time, and sometimes you can tell based on that maybe what's potentially causing your model to crash before you get any real-time results. So that's a helpful step there too.
Yep.
To consider. So Isha, I'll maybe pass it over to you now to kind of change the direction of the conversation from the tangible understanding of what HDF files are, how we can modify what data actually goes into them within the program, and shift the conversation towards how we can potentially utilize coding software to help us even take this to the next level. So this is kind of where my expertise really falls off, and I'm going to leave it to you and Chris to kind of ping pong this conversation a little bit.
Well, Ben, I think you can certainly ask good questions and provide input. But yeah, I was kind of thinking about when I've used HDF files instead of just using the default RAS output. And do want to clarify that there's a lot of scenarios in which you don't need to go to the HDF file level. RAS does have a really good way to look at outputs for 1D models, for a lot of the use cases for 2D models. But when you do want to use HDF files, it's oftentimes just a volume thing. You have a lot of data you need to look at. Maybe you want to look at the same data over and over. That makes it kind of hard to keep clicking on points and maybe plotting water surface elevation for multiple plans, multiple locations. Or maybe you want to keep looking at the same type of information across multiple projects. Other times HDF is really nice is when you want to kind of have that unique output that we talked about. And if you maybe want to just go ahead and have that plotted or formatted in some specific way, I think going straight to the HDF file is really valuable. Yeah, I don't know, do y'all have any kind of standards for when you go to use HDF versus?
Well, yeah, I mean, nowadays it's so easy to get specific output right in RAS Mapper that I don't use the HDF file or viewer to get that data as much anymore because it's so easy. It didn't used to be so easy to get that data out. But I would say for me, it's if you want something that is like you list here is not standard HEC-RAS output. Maybe you have a special way you want to compute shear stress, or you have a certain parameter that is desired for habitat evaluation. You can go in and you can pull your water surface elevation and face velocity, or some of these other parameters that aren't there by default, but you can add them in as options if those work for you, and then manipulate the data yourself using Python, or at a really basic level, you can copy and paste out of the HDF file into Excel and do manipulation right in a spreadsheet. But Python, as I'm sure you'll agree, Isha, is a much more powerful way of doing that.
Yeah, I think it keeps it really clean, kind of reduces the human error involved. Of course, there's room for other human error, but
yeah, and I'll give everybody a hint too that Isha taught me about, but Python makes way better plots. Just cleaner looking and just more professional looking than you can get in Excel. Sorry,
That's
Microsoft,
true.
but Python's got you beat there.
It's so true. Every time I make an Excel plot, I cry a little inside. But
you almost made me spit my coffee out when you said that. That was funny.
But before we get into that, I kind of just wanted to do a brief like chat about Python. I don't know. I'm certainly no Python expert, so I want to make that clear. I've just kind of learned Python by trial and error, a lot of winging it, probably a lot of messing up, but I think I certainly don't know a lot of the intense Python stuff. I do a lot of the data processing, data analysis, GIS kind of stuff, which Python is great for. So I think that's still valid.
I think that's a really good thing to mention too, because I think there are a lot of people who are a little intimidated by Python, myself included, because they have this impression, well, you have to be a computer science expert or you got to know, programming code. But you're saying, hey, I taught myself this basically.
Yeah, I taught it to myself in grad school and, only messed up like 15 times and like broke my computer a couple times, but not to scare you. But yeah, I think there's a lot of free resources, especially for Python. It is open source. It's totally free to use. Like basically every library on Python is free to use. Lots of great resources. I'd start with YouTube, like infinite numbers of intro to Python tutorials. But I know I really like, if you do have some money you want to spend, or even going their free version. I love Data Camp, especially for this data science kind of stuff. I think it's a really great kind of way to sit down, be able to try things out and kind of learn while you're like, basically you get your own little coding environment on the browser. You get to, it'll like check your work, be like, no, you need to do it this way. I think it's a really great way to learn all of these data science things. I think Python are all great resources. I kind of know R. I'm not that good at it, so I won't speak to that much. Yeah. I think the other big thing is with a lot of coding stuff is you don't have to know how to do it. You have to know what to Google. So
what do you think about using large language models like ChatGPT to help you code? Have you used that much, Isha, and how has it worked out?
I've done it a little bit. I think it works great. You definitely want to make sure you understand what it's doing. You don't want to just take some code that you can't kind of process in your head, and maybe you get an example, you go back, you kind of do some research on what some of the libraries and stuff are doing. I love it. I will also say I love figuring it out. So I'm kind of like, dang it, I don't want to have to use ChatGPT because it's faster. Because sometimes I love just getting in there and having things fail on me 50 times, then you get it on try 51. But
yeah, to me it seems like it's a lot like technical writing, where if you can write a report or a memo on a particular technical topic, then I think using AI like ChatGPT to help you write it faster is a reasonable approach. But where you get into trouble is if you are using AI to do something like write a report or write some code that you yourself don't have the ability to do. And then that means you can't review it for its accuracy, for its applicability, for other things. So I think that's the big differential to me. Chris, I don't know if you agree with that.
Yeah, I think that's a really good point. I mean, everything you produce, you want to make sure you're producing something with the highest degree of quality. And how do you know if you don't know anything about the code that you're using? So yeah, it's a great way. I like using it to get me over a hump. I just can't figure out how, there's got to be a way to do this, besides me writing, 20 pages of code. There's got to be somebody who's put together something that, a library that I can steal some code from or whatever. And that's a great way to, or ChatGPT or other large language models, great way to help you get over those hurdles. I feel like it's a very similar thing to when I started coding way back in the day, way before you guys' time. And I was using VBA and Excel, and I used macros to learn how to write code in VBA. And macros, you'll just perform a bunch of tasks in Excel while recording them, quote unquote, recording them, and it would write the code for you. And then you can go look at the code and go, oh, that's how I tell RAS to move from this cell to that cell, or to, put change the setting here or whatever. You can get that all just by recording a macro. So it's kind of like a new modern version of that. So, but I agree with you, Ben, 100% that, definitely know what it's spitting out. If it helps you get over a hurdle, great, but understand what it's telling you, or what the code is that was written for you.
Yeah. Now I know we're kind of getting knee deep into some of the coding conversation, but I'm sure there's users out there thinking, what's the real reason that you would want to use Python for evaluating or processing HDF output? So Isha, is there some examples or some particular situations in which maybe this is helpful to be able to do if you are a RAS user?
Yeah. So I kind of came up with a list of a few different examples that I've used Python. Some of them were way more intense than others. So the first one was pretty simple. Chris and I were working on a breach model, and we were unable to get the peak breach flow out of the RAS outputs. So no matter how small we got the interval, we realized that the peak flow wasn't being captured. And so what we did is we wrote computational level output, and then just had a really simple script that pulled the computational level breach flow time series, and it found the maximum and just spit it out. And so that was a really interesting tidbit of hey, sometimes RAS isn't giving us the full picture of the answers, but there's a little more information if you dig a little deeper.
Mm-hmm. So this was to look to get max flow everywhere, regardless of time, but just, what was the maximum flow that happened at every single cell, and at the computation level. Yeah, you can imagine at the computation level how many records you have in that HDF file. Trying to find those manually would be a chore, to say the least.
And that was maximum flow at each cell or each cell face?
It was actually the maximum breach flow.
Okay.
So.
Oh, sorry. Okay. Yeah. I was thinking of something else, but yeah, max breach flow. Yep. Okay. So not at the cell, but going through the breach opening.
Going through the breach opening. It just wasn't being written in RAS mapper or in the stage and flow hydrograph windows. So we just needed to be able to replicate what McBreach was telling us about what the max breach flow was. So that was kind of interesting, pretty simple. I think the next one was actually really cool, and I used some of the examples in the code I have to share today. But we had a model that we had to calibrate at multiple different flows using some shape files of level loggers. So what we were able to do is have Python go in, read the shapefile, and figure out what cell was attached to each location of level loggers, and then go into the HDF file and read the water surface elevation and velocity data for each of those cells, plot it, and export it to an Excel file and compare with the calibration data that we had. So that was a really efficient way to do it because we kept changing geometries, multiple geometries. So each of the cell numbers kept changing. We kept making tweaks to the model. And so, every time you recompute that 2D area, you're changing your cell numbers. So to keep going in each time and pulling all that data for, I think it was upwards of 20 level loggers was kind of a pain. So we got Python to do it really fast. I think it was a great use of it, and definitely kind of fun to have that pulled together.
Very cool. Was that a difficult code to write?
I think it was difficult in that it was one of the first times I used HDF files, so it was kind of difficult to kind of piece together all of the information of hey, where should I get this from, and how do I read through this and figure out what information it is that I want, but I think the actual coding itself is not that hard.
Mm.
That was pretty interesting. Fun fact, I think the hardest part of it was figuring out how to get Python to read the time series. The format of it took me like hours, I think. But I know it now, so we're all set.
Well, one of the trickiest things I think with reading HDF files through a programming environment is knowing the structure of the HDF file. I mean, if you remember the data tree that I was showing before. Oops, sorry. My Wi-Fi just cut out for a second. Yeah, if you remember the data tree I was showing before, there's a lot of different paths you can go down to get to data. And so you kind of have to decipher that. You have to figure that out to be able to code it into your Python script, right?
For sure. I think having the HDF file open on the side is really helpful when you're kind of piecing things together.
Yeah.
Other examples, I think we kind of talked about this one, but using the X and Y cell velocities for fish passage analyses and agent-based models that we're doing on one project. I think that's a really unique way to look at the information. So,
yeah. Are there any examples, Isha, that you can show us in terms of like how the code actually works and how you can go from, RAS results to code to product?
Yeah. Well, I kind of pulled together an example that I can go through.
Okay.
Into that. Okay. So you'll see this, right?
Yeah.
Okay. I was looking at the Muncie kind of example data set from HEC-RAS. And this is, I think, just a 2D breach plan through Muncie, Indiana. I kind of just pulled this one as an example. I don't know a lot about it, but I can pull some data from it. So here I was trying to figure out if you were in the town of Muncie during a crazy event and you wanted to figure out how to spend your Friday night, you needed to know what the flooding was going to look like, assuming you can predict the breach. You can kind of piece together where it's safe to be and what you can walk through. So quickly, your
I
options.
do this every time I go out to dinner. I always check the flood maps.
There you go. So you have some options here. You can go catch a high school football game. You can go to Elm Street Brewing. You can go to Madison Park. Or maybe you're very cultured and you can watch a play at the theater. So just for reference, if we just like play this.
Where would you likely to be on a Friday night, Ben? Of those options?
Probably the brewery, which means I'd be wet.
I know Isha would be at the theater.
I'm not that cultured.
You're not? Oh, okay.
So say you don't want to run this entire simulation. You just want to look at the results in your little Python HDF reader. We can pull them in. So how we would do this, set up your Python so that you import all the necessary packages. I think a lot of these are pretty straightforward. They're pretty common data processing tools, pandas, numpy, matplotlib, datetime functions. But the important one here is this H5Py. This is what's going to help you read your HDF file.
And these are all just available, like you can find them online, or where do you get all these libraries?
Great question. So I like to use Anaconda Navigator. So if you can just download this, it's open source. Well, it's not open source, it's free. And you can kind of set up your virtual environments in here, and then you can manage your environments and add all of your different packages. And go in and use all of these nice platforms. I love Jupyter notebooks. I love using Spider for other types of scripting. Yeah, and it'll all be kind of set up in there for you. And it's a much better way to manage your packages rather than downloading them yourself.
Yeah, and for those of you who are not very familiar with coding or Python coding, each one of those libraries has its own like library of code that you're borrowing basically. So, you got two options. You can write all that, figure it all out yourself, or hey, use what somebody else has already put together. And
yeah.
Yeah.
And I will say these are all very standard, very common. Using Python without some of these would be a totally different game. So yeah, so we could just run that, and see it's run because it's a little number in there. So now we have all of the libraries loaded into our code, and then we pull in the project and the input variables we have. So I have this HDF path variable over here that just links straight to the plan HDF file. That's where I'm going to read the results from. And then I also specified the name of the 2D mesh, just because that's one of the inputs into the HDF file. Similarly, what I did for this project, just to keep it simple, is I created a dictionary with the cell numbers for each of the locations we want to look at, just so we can kind of point the HDF, like point Python to read what we want out of it.
That's really clever. What did you call that? A dictionary?
Yep. So a dictionary is kind of a standard variable type in Python where you have like a key and you have a value. So the key here is a cell number, and the value I put as the name, just so we can reference it later.
Okay.
Yep. And then all I did here is I just kind of translated this dictionary into a data frame. So kind of like a spreadsheet table, just so we can kind of help start populating some information. So I can go ahead and run this. Nothing crazy is going to happen. It basically just defined these variables with the paths and the names and the cells that we want. And then this is kind of where we start getting into the meat of the code. So I have a couple different functions here that I've written. This first one is called fill cell minimum elevation. So what this one does is it goes into the HDF file and it pulls out the minimum elevation for each of the cells. And this is helpful because we're pulling water surface information. The HDF file, if your cell is empty, or I guess if it's dry, it just writes your minimum elevation instead of the water surface. So we want to make sure that we can compare them and make sure that there is actually water there and it's not just dry. So what this is going to do is just pull it in. This is the main function for reading the HDF file. And then goes through and reads the geometry, 2D flow areas, and then we're filling in the mesh name, reading the cell minimum elevation, and then populating it in our data frame. Pretty straightforward. Similarly, we're going to go into the water surface elevation, read the same thing. The difference here is that the water surface elevation is a time series. Cell minimum elevation doesn't change over time. Water surface elevation has a time step associated with it. So go in here, put in our results path. So this is kind of something that's helpful to figure out ahead of time. Python will probably give you errors if you don't have this figured out correctly. It'll be like you can't read this HDF path. So that's where it's really helpful to go into HDF view, figure out what it is you want to look at. Similarly, filling in our mesh name, and then we get results.
I like the comments you have in there because I think that's super important. I mean, not just for presenting it on a podcast like ours, but for you going back, years later and wanting to use this again and going, well, what the heck does this code do here? But having lots of comments in there can really help refresh your memory. Or if you got to give it to somebody else, they can see what you were doing too.
Absolutely. I was honestly pretty proud of myself that I went back to the original code that I pulled this from, and I was like, oh, I already wrote comments in there.
Nice.
Yay.
Yeah, it's not, it doesn't always happen that way for me. So this is kind of a stellar example on my end.
So
Mhm.
once you execute a script like this, what does the results look like compared to what you have in RasMapper?
Okay. So the results can kind of look like whatever you want them to look like, right? So if I just run everything here, I end up, this is just kind of a clip of the table that I have, but I have a time step as my index, and then I have columns with each of my cells, and it has the water surface elevation. I told the script that if the cell minimum elevation is the same as the water surface elevation, I want it to write in a nan, just so we don't get kind of confused with our results. And then if you take this information and you want to plot it so you can see it really easily, come up with a really nice plot of what the water surface looks like over time. So I know, Chris, you kind of mentioned the plots in Python look a lot better than Excel. This is a great example of that, even though it's pretty straightforward.
Yeah.
So we can kind of figure out like, hey, Madison Park and Elm Street Brewing and the high school football field are going to start flooding. But if we went to the theater or the cupcake place, we're going to be in the clear.
Very cool. You can also see
So-
it looks like your timing a little bit on that too. Madison Park starts flooding a little bit first, and then Elm Street, and then the high school football field.
Yep, exactly. So obviously there's like infinite ways to look at this data. And this is just like one kind of far-stretched example of a Friday night plan. But you can kind of look at things in as many ways as you want. So you could be looking at velocities, you could be looking at depths, you could be doing some type of post-processing on this data. So for instance, maybe you had depth data, but you only cared about where the depth was greater than 2 feet, because that's what you can walk across. You could filter it. You could potentially even map it yourself if you wanted to create some different types of mapping products. There's a lot of good GIS libraries in Python as well that can help you do that. Yeah, I think kind of just a cool way to re-envision the kind of outputs you can get from RAS.
And is it fair to say that this example, like you said, it wouldn't be time prohibitive to do this just yourself within RasMapper? I'm assuming it probably took more time to write the script than what it would do in that particular case. But where you would potentially utilize something like this is if you found yourself having to do this for multiple plans, multiple models, and you're adding up the time in your head about how long this is going to take you, and you're like, well, maybe this is the opportunity to write a script to have this kind of automated, or maybe this is a process that you implement for many of your project types, and so it's something you could use over and over again in the future. Those are the type of situations where maybe you would consider jumping into this.
Absolutely. But I also just want to say that when I pulled this together from a previous script, it took me all of like an hour, including writing a bunch, of the rest of this. So once you have it written, it's really easy to just go in here and adjust this results path to whatever it is you want to look at.
Okay.
And then it'll just kind of plot whatever you want. So there's a lot of ways to do it. I think some of the other things that Python can do that RAS can't do is just iterate. So say you want to look at 3 different models that are located in 3 different folders, and you want to plot everything on one graph. That's super easy to do here. Whatever reason that would be that you would want to do that. Say you want to compare some models. You want to say, hey, why do I have multiple versions of the same model? What are the differences in the results? This would be a really easy way to see that. So you can kind of build on the basics here super easily. I also want to just point out, because I referenced this, the date time stamp in the HDF file, you have to use this very special shape called S22. And that makes reading it very easy. I don't know why.
So is it because it's stored in like Julian format or something?
Yeah, I think I don't remember the specifics, but I know it took me, like, all of this code is just to get the time
in a usable format.
In a usable format for Python. So just something to keep in mind. I mean, I'm happy to share the code.
Yeah, I think that happens in a lot of other areas too in the software, that just in the base code of HEC-RAS, they like to store date times in a kind of a number, which I think is called Julian or something like that.
Yep.
And yeah, it's, unless you have that conversion, it's really tough to work with.
Yep. But I mean, Python does make it pretty easy.
Yeah.
There is probably a way to write this a little faster, but
very cool.
Yeah.
Well, we only have a few minutes left, and I do want to leave some time for some trivia here at the end. But before we transition there, Chris or Isha, is there anything else that you wanted to kind of add to this topic? Again, you could probably have a standalone class on using Python to process RAS results, but anything important to add?
Well, I just want to say, I think anytime you have an idea of automating a process in RAS, whether it's you have 90 plans that you want to run, all of the plans, and grab one bit of output from each one and store it in a spreadsheet. You wouldn't ever want to do that by hand. It would just be a nightmare. And so writing that to me, correct me if I'm wrong, Isha, but that sounds like a very, very short script to do something like that, right?
Absolutely.
Very easy. Might take you, obviously, if you already know Python, it's going to take you a short amount of time. If you need to learn Python, then you got to learn it. But if you already know Python, I mean, you're going to write that script in 5 minutes, and then you can press the run button and go home for the day. Come back the next day, it's all done.
Might not even take that long.
Might not even take that long. That's right. Depends on how fast your RAS models run. And yeah, so if you think, if you have this thought in your mind, oh my gosh, this is going to take me forever to do this thing in RAS, and there's a lot of repetitive stuff involved, this is a great tool to solve that problem for you.
Yep. And I think what I will add to that is, if you have time or want to play around with this, even if you don't have an application for it right now, I would encourage you to kind of have some building blocks set up. So for instance, Chris, your suggestion about pulling the same data for 90 different plans, that would be like adding 2 lines here. So once you have these basics kind of saved somewhere, you can go in and make a lot of changes really fast and pull a lot of stuff together.
So you start building your own library, right?
Yep.
And then you could call it like Isha Pie or something, right? And share it with everybody. Yeah, and there's a really good community out there of people who share their Python code. I mean, that's part of Python coding, is sharing and borrowing from other people and improving on other things. And if you look hard enough, you'll find there's a lot of RAS related open source Python code out there that you can get from GitHub or something.
Good stuff. Well, great conversation. Thank you again, Isha, for taking the time to share some of that with us. If you have questions for Isha, or if you want some of this code that Isha developed, feel free to reach out to her directly, or leave a comment in the YouTube channel, and we'll do our best to respond to you. Isha, I also don't know if you knew, but you are the first woman that we've had as a guest on Full Momentum. So congratulations on breaking that long overdue barrier that we've accidentally employed on the podcast. So we have a couple other gals that are lined up to be on the program this year, but you are the first. So congratulations.
And
congratulations to y'all, I think.
Yeah, exactly. And coincidentally, I think we were told before this that it's International Women's in Engineering Week. Is that correct?
International? Yeah.
International Women in Engineering Week. So coincidentally, but definitely worth noting out there.
Awesome.
Yeah. So what do we got for trivia here?
Yeah, so I think that to end the segment here, just a fun little trivia opportunity, so we can each go through and ask ourselves a question here. No pressure to stump everybody, but I'll go ahead and start, and then Chris, we can go over to you, and then Isha, if you wanna close it out. So, my question, and no cheating here, you can't jump into the manual. My
I got my
question is around
ChatGPT ready.
hydraulic computations through gated spillways. That's the topic of this particular question. So frame your mind with that.
Okay.
All right. So, as you all probably know, when the upstream water surface upstream of a gate is equal to or less than 1 times the gate opening, the flow through the gate is calculated as weir flow. Okay. So if it's equal to or less than 1.0 times the gate opening, then it's calculated as gate flow. There is a transition zone between 1 and this upper limit where it's actually computed as weir flow and gate flow, and the program kind of balances out and actually iterates and comes to a solution. And then above this certain depth, it's the gate flow equations are applied. And so again, I'll just read it directly from the manual, and then your guys' job is to fill in the number. So when the upstream water surface is greater than or equal to X times the height of the gate opening, the gate flow equations are applied. What is that number? Might be a little bit of a guessing game.
It's gonna be a guess for me, because I don't know off the top of my head. But Isha,
if
do
you
you know
that would be
one?
impressive. So
Yeah, I'm also guessing.
okay, well, Isha, why don't you start us off?
I'm going to guess 1.1.
Okay, 0.1 times the gate opening.
I have a feeling. So I have a feeling you're closer than my guess, Isha, and I don't know why. I just have a feeling.
You should go closer to her guess then.
Yeah,
I know, but
You can't caveat that because you're trying to take credit for her guess and your guess.
I'm gonna play this trivia game honorably and go with my initial number, even though
gotcha.
now after Isha said it, I want to change my answer.
Okay.
But I was gonna say 1.5.
Okay.
But I think that's too high. I think that's way too high.
So the answer is almost smack dab in the middle. So it's 1.25 times the height of the gate opening is where outside of the transition zone.
So by Price is Right rules, I guess you win that one, Isha, because I went over. So
yeah.
And then the dam failed and the gate broke and everything. Yeah.
When it's in between 1 and 1.2 times the size of the gate opening, the flow in that zone of transition, the program computes the upstream head with both equations and then calculates a linear weighted average of the two values. And that's an iterative process. So I thought that was an interesting one to share.
That is an interesting question. I want to ask you guys, have either of you seen this happen on a real project, this transition from free flow to gate flow?
I would assume it happened on the Carpenter project that we were working on, right, Isha?
Yep.
Yeah.
Yep.
Yeah.
Well, I also feel like sometimes it happens. I feel like there have been times where for like a lower flow, I've gotten one number for the upstream water surface elevation, and then for a higher flow, it's been like really close, or like it hasn't quite aligned as you think it would. And a lot of times it's because it's transitioning between weir and gate flow.
Yeah, but what I mean, have you been out and actually seen this in person?
Oh, I don't think I have. No.
So it's actually quite interesting. It can be a very violent process switching from free flow to gate flow. There's a lot of fluctuation. And so it's good they use that transition because it's not just an immediate, okay, boom, it's weir flow, now it's gate flow. It'll bounce back and forth. You get a lot of splashing, a lot of what they call burping sometimes, where air that gets trapped gets kind of pushed out, and that's usually when you have more of a tunnel downstream of it. But yeah, it can be really kind of very non-steady, very what's the word I'm thinking of?
Ununiform.
Yeah, non-uniform for sure, but more time-based, just changing. Transient, that's what I was thinking of. It's very transient, a lot of bouncing around, and then it'll all of a sudden get to gate flow and it'll just settle out and be nice and calm again. So
interesting. Yeah.
Yeah.
All right, Chris, what's your trivia question for us?
All right. I hope you guys get this right.
Yeah.
Because we deal with this all the time.
Oh boy.
He always does.
Caveat that.
But I want to know what the E and the L and the M stand for in ELM, like as in shallow water equations dash ELM for the equation set.
I know this, but Ben.
It's always hard for me to pronounce the E. It's your
Eulerian?
Eulerian Lagrangian method.
Yeah, that's it. Is that what you were going to say, Isha?
Yep.
She was
I was going to
copying.
pronounce it correctly.
Yeah,
I think I don't know. I've heard.
I'm actually glad I went first. So
I've heard Eulerian and I've heard Eulerian. I've
Okay.
always said Eulerian, but I honestly don't know which is correct.
Yeah.
Eulerian, Lagrangian is
Professors
easier.
told me Eulerian, so that's what I got.
Eulerian,
Lagrangian.
Euler. Yeah, it's by Mr. Euler, Dr. Euler, probably.
Yeah.
And Dr. Lagrangian or Dr. Lagrange. Yeah, I remember that name coming up a lot in like physics and class, Lagrange.
Yep.
Well, and Euler too, for that matter. But
yeah. All right. Cool.
All right.
Isha, close this out. What's yours?
All right, Chris, this was specially made for you because we spent a lot of time talking about this earlier this year. When RAS computes turbulence, it models it as a gradient diffusion, and the diffusion rate of turbulence is the eddy viscosity. There are two terms in the eddy viscosity equation. What do each of them represent?
two terms in the eddy viscosity equation. So there is the
I wouldn't know this one.
There's the oh gosh, lateral and longitudinal turbulence, right? And then so that would be your diffusion coefficient. Both lateral and longitudinal are in that part of the equation. And then the other one is the Smagorinsky, right? Which is like the edge effects, the turbulent edge effects.
Those are the RAS inputs.
That's what? Sorry?
Those are the inputs into the RAS model.
Yeah.
But there's two
that
terms.
wasn't your question.
Maybe that should have been my question. Well, I guess I made this hard because Chris, you said you were going to try to trick us, so I wanted to.
I didn't say that. Ben said that.
Well, there's two terms. I won't read them out loud because they make no sense. But the first term is the vertical shear component, and the second term is the horizontal shear component. They sum up to be the eddy viscosity.
Okay.
Okay.
So eddy viscosity, the equation for eddy viscosity is made up of those vertical and horizontal shear, you say? Okay. Components. Oh.
So water spinning this way and this way, right?
Yeah. Yep. Okay. Cool. Those were all great questions. That finishes out our trivia segment for today. So we are just about at time. Want to again thank Isha for joining us today to talk through our 10 commandments of HEC-RAS modeling, talking through HDF files and using Python to kind of maximize the utility of those files and the utility of extracting results from them. And then for putting up with our trivia segment, which is always a little bit of an adventure. So thank you, Isha, again for joining us.
Thanks,
Chris,
Isha.
Yeah, thanks for having me.
Thanks for co-hosting as always. This has been episode 32 of the Full Momentum podcast. And we will look forward to talking to you all next month on episode 33. So thank you all for joining us today. Until next time.
Bye, everyone.
See y'all later.